So hello, and welcome to my talk on what functional programming can learn from static introspection. So first of all, I hope everybody can hear me. What is static introspection? So it's the ability to reflect on your Compiletime environment. So asking things like, what is the type of this thing? What field names does this record have? Things like that. And it's also the ability to go as far as to say, does this arbitrary expression even compile? So if I have something like, quote hello plus 1, does this expression compile? And check that at compile time. And if it compiles, do this one thing. If it doesn't compile, do this other thing. So it's the ability to, based on the static environment, to conditionally generate code. The second big arm of this is what's called Compiletime function evaluation. So that means that you have some term level language that's available to you, like the normal languages that you use to get everyday stuff done, and there is a subset of that available at compile time. So what that means is all of your for loops, your while loops, your functions, your assignments, things like that are available at the compile time level. And when you put that together, that means that you can use those constructs to query your compile time environment and ask those questions, what is the type of this thing? Does this thing compile? And conditionally generate your code. So I'm going to argue that typed functional languages like, sort of the Haskells and the OCamls really need this. Scala has this already to a certain degree, but I think more languages should have it. So one of the big, one of the big touted benefits of compile time evaluation and static introspection is performance. So if you Google either of those terms, you're going to see lots of talks and articles on how to make your code fast using these two techniques. While I think that is important, I think that that's probably sort of the least interesting part of either of those two things. So, it does work. What you do when you're trying to get performance out of this code is you end up playing the optimizer. Like you become the optimizer, you become the JIT compiler, right? But I'm going to show in a couple of examples that even though you have all of these techniques, there is no silver bullet. You can have compile time evaluation and still have slow code, or still have a buggy code base, or still have a bad code base. I think that the thing that these two techniques really bring to the table is it makes type level programming, compile time programming, utterly boring, right? It makes it accessible, it makes it maintainable, and it makes it possible. And yes, I say possible knowing that there are Turing complete type systems out there, so technically everything is possible in those systems. But when I say possible, I mean something that you would reach for and just try out for a couple of hours or just take a weekend project. It's very difficult to do in other languages. It is a whole lot easier here. And this other big thing is you have this idea of type level querying. Like you can query your code base as though it was a database. So you can have library level and project specific tooling, very, very granular tooling that is just for the problem at hand. And you can have customizable compiler feedback. So with the Haskells and the OCamls and things like that, what you have is language level feedback, and the more expressivity you throw into those type systems, the less good those error messages and diagnostics are going to be, for the simple reason that the language can't possibly know what you intended. Here, library authors know what you intended and can control the error messages and the diagnostics such that they can give you something with a little more semantic meaning than what the language could possibly give you. And I think those three things are huge and, in my opinion, are much more important than performance, which kind of falls out of that to a degree. So the examples I'm going to show you are in NIM and D. NIM and D are not functional programming languages. So just spoiler alert, they're not functional. They're imperative languages that come from the C++ and sort of Ada tradition. D comes from C++, NIM comes from Ada. It looks like Python, but it kind of comes from Ada. So I'm going to, I'm also going to frame this in real-world examples. And by real-world examples, I mean things that have been a pain in my butt in exactly the last 6 months. In the last 6 months, all of the examples that I'm going to show you have been a royal pain, and if I had these two things, they would not have been a royal pain. And by the way, I do work in type functional languages for a living, so it's not like, you know, I mean, yes, we need these things. Uh-oh, I guess everybody's coming in now. And what I want to also say is that this is not a NIM or D evangelism talk. This is a learn, not adopt, right? So NIM and D are great languages in their own right, and there is an evangelism talk for them, mostly probably related to something like C++ interop. But this is more about taking those techniques and moving them into type functional languages in a way that makes sense for type functional languages. So it's not blindly copying, it's sort of adopting and cross-pollinating and sort of seeing what makes sense. So just to see what we're looking at, this is what compile time evaluation looks like in NIM. It's just a method called say hello that says hello world, right, sort of. But it's much easier to see what's going on if you actually compile the thing. So what's going on is when I'm compiling it, that's what nimc hello.nim does. It's printing out hello to Lambda World at compile time. When I run that executable, it's printing hello to Lambda World at runtime. So at compile time, it's printing out one message. At runtime, it's printing out a whole different message. So something's going on where we're able to get two different behaviors at compile time and runtime. So there's this. So how we do that is very simple. There's this function called say hello that takes a string and outputs a string. Oh, and by the way, for this talk, I'm kind of going to assume a little bit of familiarity with either Python-like syntax or sort of curly brace semicolon-like syntax. So I apologize for that. So there's a function called say hello that takes a string and outputs a string, and the magic is happening in that when nim VM line. So that is a static conditional where nim VM is true when you are in the compile time phase. So when you're in the compile time phase, there's a version of this function that's generated that says hello to Lambda World at compile time. Otherwise, the version that's generated at runtime is hello to Lambda World at runtime. So inside of that static block, I say hello to Lambda World at compile time, and inside, you know, in the standard echo at the top level, I say hello to Lambda World at runtime. And this is static introspection in D. There's no real reason for this to be in D and not in NIM. They can both do pretty much the same thing. In fact, both languages overlap a lot more than they differ, in my opinion. So this is a struct in D. If you're familiar with C++y type code, this should hopefully look somewhat familiar. So I have a struct that has two members, an integer and a string. They're called an int and a string. And I have a compile time message that says, hey, at compile time, reflect on the shape of this struct and print out all of the members. So at compile time, it prints out a tuple of an int and a string, which is what those two field members are. So I can go further and I can say, hey, get me one of those members. So this is saying, look inside that struct S and get me whatever member is an int, and then give me the type of that. So it's iterating down the members of the struct and finding one called an int and saying, get me the type. And that's what this does. So when you compile it, at compile time, it's handing you back the type of that integer. It's printing it out to the screen. And if you try and get something that doesn't exist, so here I'm trying to get a member called foo. Foo does not exist inside the struct. You get a compile time error message that says that there's no property foo for type S. So even though we're dealing with strings and, like, you know, maybe some of us like types and don't like strings, and like stringly type programming is bad or whatever, like at compile time, those strings are checked. So there's some level of safety there. And just to convince you that this isn't doing some kind of like, like cheesy, like, getting the text blob of that struct and then like regular expression through it and like find the fields and all of this stuff. It's not doing that. So I'm changing the struct to a class. So when I change the struct to a class C with the same fields and get the same members on it, it's printing out not just an int and a string, it's also printing out toString, toHash, a comparison operator, an equals operator, and a couple of other things. So this is actually doing some kind of semantic analysis. So like when you create a class, it inherits all of these members, and it's printing that out for you. So this is just to convince you that it's not doing something like ad hoc with the AST itself. So let's now talk about the supposed performance advantages of compile-time function evaluation, because this comes up a lot. So here I have a very small NIM method that parses the CSV, a comma-separated value file. And this is doing it at compile time, but it could also do it at runtime. This method is in no way like, just compile time. It works in both phases. So it's reading this file called large CSV. This file has 21,000 lines, and it's about 2.4 megabytes. So it's a moderate-sized CSV file. It's not huge. It's not small. It's non-trivial, right? So it's reading that in at compile time. That snippet of code took 10 seconds to compile. 10 seconds is a lot, by the way. And you should expect something like that because you're making it do a lot of work at compile time. It's reading all that stuff in. So you should expect that. And also, in the resulting binary, the lookup of that CSV is instant. It's not even measurable. So that means that I can find the bottom row of that CSV file in nothing. I don't even know how much time it takes. But I'm going to argue that performance is not always worth it. Because remember I said that this was a 2.4 megabyte CSV file? Once that got baked into the binary, that turned into a 22 megabyte binary. A 22 megabyte binary that was stripped down to 16 megabytes. That is still a huge difference. And when I changed it from compile time to runtime, so it takes 5 characters, by the way, to change when a function runs. So instead of const parsed equals like read CSV static read, I just go let parsed equals read CSV read file, and everything else stays the same. Compile times went down from 10 seconds to 1.5 seconds. That's still a little on the high side, and I have to figure out why, but that's still almost an 8 to 9x decrease in compile times. And the initial runtime parsing of that CSV file took under a second. So what that means is that by using compile time evaluation for this particular example, in my opinion, we've lost. We haven't gained anything. We've lost a lot for that instant lookup. And Dee's std_regex is kind of the same way. So std_regex is a regular expression library that ships with the D standard library. And it has 2 modes. It has a runtime mode and it has a compile time mode. In the runtime mode, you just go R, open quotes, and put the regular expression in there. In the compile time mode, you use this thing called ctregex, which is a compile time function, and the regular expression goes inside of those backticks. So the idea here is you generate a highly specialized compile time engine for just exactly that regular expression. And that's where they think that performance comes from, right? So I ran this on a primality tester regular expression. By the way, this is really cool. This is a really cool regular expression. It was invented by a Perl hacker named Abigail about 20 years ago, I think in the 2000s or so. And basically what it does is it takes a string of 1s. And if there's a prime number of 1s, it fails. It fails to match that. If there's a non-prime number of 1s, it succeeds. So this is a negative tester. If this regular expression fails to match, it is prime. If it matches, it is not prime. And the reason I chose this is 1, it's short, and 2, it backtracks a ton. So like when you have this regular expression on a large prime number, it backtracks exactly that number of times at least. So I tested this on 104,729, which according to the internet is the 10,000th prime number. So it's backtracking at least 104,000 times. And unfortunately, both took about 2.5 minutes to not match, because that is a prime number. So both in the highly optimized compile time regular expression and the runtime regular expression took exactly the same amount of time. So there was no difference in performance, and that's disappointing. So I think the takeaway here is that performance is hard, and compile time evaluation is not a silver bullet, and you take on a lot of compile time increases for a one-time runtime hit, if you can afford that. And you get increased binary sizes. So if you're going to do compile time evaluation, you really need to, I think, measure your needs and make sure that it's actually working for you instead of against you. But the real MVP here is that all of this stuff goes through common code. It's not two different code paths like this one is for compile time regular expressions and that one is for runtime regular expressions. It's all the same code that toggles at the drop of a hat. So what this means is that this kind of measurement that I showed you is actually possible. At the worst, you lost a couple of days of work, and you still have a runtime library at the end of the day. How would you even go about attempting this in another statically typed functional programming language? Would you even consider doing a compile time regular expression engine in type level Haskell? Like on a type level string literal or something like that. And even if you had the persistence and the will and the pioneering spirit to do that, once the measurements showed that there was no advantage to that, would you have like the intestinal fortitude to throw it away? Like I don't think I would. Like I'd want to get at least like one conference talk or a paper out of it, at least. Like I couldn't throw that away. But what easily switching between compile time and runtime does is it lets you make those measurements without having to really think about it too hard. So I think that's an advantage of this, is that you get these metrics. So the second thing I wanted to talk about is this idea of fast lookups. Now this is about sort of more developer experience than it is about programming. And it's looking up, say, like the fields inside of a record in a domain-specific way. So this is an object in NIM. An object is not an object-oriented type object. It's just an extensible record. That's all it is. So I have an object called O1, and it's got a few fields. And the way these fields are named are pretty typical for like sort of a production code base. Like things evolve over time. You don't always follow naming conventions. So sometimes you have to stick like an O1 in front of all the fields because there's some languages that make you do that, And sometimes, one of them has a user underscore ID, user underscore address. One is just an age, not a user underscore age. There's an IDs, but IDs is capitalized for some odd reason. So there's like this mix of like naming conventions. So now I want to gather up all the fields and all the types. And this is just NIM code that does that. This is almost the same as that D code that I showed you earlier. There's a function called gather fields that takes a meta type, that's what type desc is, a type description, and it outputs a list of string tuples. It just iterates over that object and sort of tacks on the name of the field and the type of the field into that sequence. And when I run it at compile time, I gather all those fields and echo them out to standard out. And when I compile it, I get this list of fields inside of that object. So you're saying, big deal. Who cares? My language REPL is enough. GHCI can do this right now. Just go :I, it'll print out all of these fields. What have I really gained? Okay. How about this? It's late in the day. It's been a long week. Okay? I have to deal with about maybe 10 to 12 of these in my head, of these objects in my head, I don't know, for any given task. I have to know about, I have to know the insides of 10 to 12 of these. I know that inside of this object there's a field called IDs. It's got the string IDS in there somewhere. And I know that it's of type sequence of integer. But I really don't want to have to bother looking all this stuff up because it makes me nuts. I just want the computer to tell me it already knows this stuff. So we can just filter it. So we gather all the fields and run a standard filter function on them. This is just a standard list filtering function that you have in JavaScript and Python and tons of other languages, and it works at both compile time and runtime. There's nothing like, compile-timey about this specifically. I filter those fields and look for, in that first of the tuple, I lowercase it and look for anything that contains an IDS. And in the second of the tuple, I look for anything that is of type sequence of int. And when I run that at compile time, it spits out the field that I want. So what this does is allow you to make very granular domain-specific tooling that fit your project, maybe even that very task that you're working on at that moment. These aren't like, big, hugely engineered tools. These are tiny throwaway tools that do one thing, and they do it in that one very specific instance. You may create hundreds of these. To get something like this would take a lot of work in an IDE. So IntelliJ, I know, actually supports things like this example that I'm showing you right now. So in IntelliJ, if you go O dot and start typing things, it'll actually fuzzy search inside of those, inside of the fields, inside of the field members, and actually do some level of type inference and make sure that it only shows you things that actually fit the type that you're looking for. But look at the amount of work that IntelliJ has to do that. And look at the amount of work that I just did to do the same thing. Well, not quite the same thing, but in essence the same thing. And another big idea, and I think even if you don't care so much about the developer experience, this is something that I bet some of you have had to deal with, is this idea of data type diffing. The moment you start modeling your domain in a sum type, in an object, in any one of these like recordy type things, you're going to end up in a place where you want to version two different versions of these things. Like you have version 1 of this type, and now you have version 2 of this type, and version 3 going on. And this is hugely important when serialization becomes involved. Everybody talks about how, everybody thinks like the most important problem with serialization is how fast it is. Yes, speed does matter, but what really matters at the end of the day is a robust way of doing data type diffing. What fields were added and removed between two different versions of a data type? We need to know that. So here's another object. This is O2. This is O1 evolved like 6 months to a year later. We've cleaned up some of our naming, right? Instead of like O1 user underscore ID, it's just ID and everything's nice, right? So this is version 2 of this object. That's the first object, a little messier, right? So what we need to do now in order to diff these two is actually just massage the fields of the first object. A lot of data type diffing, a lot of record diffing is really just data massaging. The same as you do with CSV files that don't quite work and things like that. So we're gathering up the fields at compile time, and then we're stripping the O1 prefix off of those fields, we're stripping the user prefix off of those fields, the underscores, all of that stuff. So we're left with something relatively nice and clean. And then we gather the fields from O2, and at this point, it's just a standard set diff. So you say, hey, what fields are in O2 that are not in O1? What fields of O1 are not in O2? And print that out for me. This is a standard set. This is part of the NIM standard library. This works both at compile time and at runtime. So when you print this out, what it's telling me is, hey, there's this new field called email of type string, and you need to deal with that. So what this allows you to do is reliably do database migration, data type migration, actually, which is just the same as a database migration. This is testable and human inspectable. And it's absolutely crucial when you need backwards compatibility with your serialization and deserialization. If your customer has version 1 of a data type and you need to support that data type from now onwards, you need to have a way of going back and forth between your versions. And currently in languages where you can't introspect over your types and your fields, this is very difficult to do. It takes a lot of type level machinery to do this. And I know this because I had to do it about 4 weeks ago. Like I said, these are real world examples. This was a pain in my ass like 4 weeks ago, and that's why I'm presenting it. So, the next thing I want to talk about is Compiletime JSON parsing. So here we go. Oops. Can everybody see that code? What? You can't see this? Oh. Yes? No? Okay, thank you. Appreciate that. Okay, so here's a standard JSON sample. So like when you say, hey, what kind of payload are you sending, your vendor or whoever it is, when they write the documentation, are going to give you a sample. Most of the time, they're not going to give you some robust schema. They're going to say, here's a sample, do what you will with it. Okay, so this is just standard JSON. It's got an ID, an age with a number field, an address, and some grades and all of this stuff, right? So what we're going to do is at compile time, we're going to iterate through this and sort of annotate the keys with the type of the thing they are in sort of a very ad hoc way. So if the key is a string, just sort of annotate it with a string quote. If the key is an integer, annotate it with an integer quote. Yes, that's right. I don't actually account for a null in here, but you get the idea. So when I run this, can you see that? Let's see. Sorry. Let me do that. Oh, well. Let's try it now. Okay, well, it went off the screen, but here's the original JSON, the sample, right? And here's the same thing annotated with a bunch of types. So this is all happening at compile time again. So I'm reflecting on the structure of that JSON and sort of giving it some ad hoc stringy types. Okay, so what is the advantage of this? First of all, you get to reflect on the structure of sample data. Sample data beats schemas all the time. I can't tell you the number of times I've seen sample data that does not match up to the schema, and what the developer implements on the other end of the thing you're supposed to send along is the sample data. They don't implement the schema. Okay, so like sample data is your king. So what it does is it finds inconsistencies. So if that grades object had, instead of 180, 50, if it had 180, 50, 33.3, right? You would see that down here. You would see int, double. And now you know that that field is actually an array of doubles, not an array of integers. And this is useful when generating things like API reports. And this is also useful when you're trying to communicate with your front-end team. I don't know how you work in your workplace, but for us, we have a back-end team and a front-end team, and the front-end team comes up to us and says, here's a blob of JSON. What does this field match up to on your end? And that's an awkwardly, sort of hard question to answer because it involves us like digging through like our source code, and we don't know exactly where things are, and the last time it was in this one module and now it's in this other module, and this kind of stuff. So this is not actually, this is a less easy question to answer currently than it needs to be. And I think it would be more easy if we had things like this to just look it up on the fly. But we can do better than that. What about compile time type reflection? Okay, so, all right, Okay, well, here we have the same sample code that we had before. ID, age, address, all of this stuff. But what we're doing is we're doing something a little different when we're iterating over it. So when we iterate over each of the fields, we're generating a tuple, a NIM tuple, right? So what that looks like is if I do something like so, what that did was take that sample data and at compile time convert it to a NIM data structure. So this is a tuple in NIM is just an anonymous record. It's not like tuples in other languages. It's just called a tuple. So here I have an ID field with a 1, 2, 3, 4, 5, an age, a street, a zip, all of this stuff. Okay, so now that we have that, we can say, hey, what is the type of that thing? Oops. And the NIM type checker at compile time will tell me, hey, that tuple looks like this is the type signature. It is a tuple with an ID of string, an age of int, and an address, which is another tuple, and a sequence of integers. And now I can use this for real work. So here I have some real, let's call this real JSON. Okay? So now I've generated that type out of the sample data. And there's this macro called to, which takes parse JSON and coerces it to a type. So you're passing in this type as sort of this first-class citizen. And when you do that, it has parsed the real data into sort of this type that we generated using sample data. Okay. Does this ring any bells? Has anybody seen something like this? A relatively successful type functional programming language has a feature just like this built in. Anybody know what it is? Sir? It's exactly Fsharp type providers. Yes. Well done. And we've just sort of been able to emulate that because we have static introspection and compile time evaluation. But here's what's not in Fsharp. So this is not just a poor man's version of the Fsharp type providers. Here's what you can't do. You cannot give an Fsharp type provider a list of samples saying, hey, get me a type that's the composite of this if you can. So say you had not just one sample, but 10 samples. In samples 1 through 9, the age was an int. In sample 10, it was a null. That means your age is now an optional field if you put those all together. How would you do that with an Fsharp type provider? And we can do that here because we have access to that kind of information, and it's not even hard. It just uses basic constructs of the language. It's things that on the value level, on the term level, would be, I don't know, a couple of hours. So you can quickly manage your external API specs this way because, as I said, in my opinion, samples are more important than the actual schema itself. And a lot of times, the samples find mistakes in the schema. So here we have a typesafe printf. So that's going. This is my next demo. I'm going to have static introspection give you a typesafe printf. This is the kind of trick that usually is sort of in the realm of like dependently typed languages. This is like their go-to example for dependent languages is like a typesafe printf or like a length index vector and things like that. So I'm going to show you what a typesafe printf looks like. So here we have a simple format string. So this is just like a string that you might see in, like C printf or JavaScript printf or something like that. Some string, %s, some number, %d. And the first thing we're going to do is lex it. Lex, by the way, is sort of an old school term that just means to tokenize something. So that's what This is just a Lex routine. And I don't intend for you to understand all that code. What I intend to show you is that it's made up of very simple constructs. It's made up of basic, like, while loops and if statements. And this is all run at compile time. So if I now do NIMD printf, wait, that should have. Okay, so what it's doing is it's taking that format specified string and it's breaking it up into a string, a format specifier, more of the string, and the format specifier. And it's counting up the number of format specifiers that there are. There's a %s and there's a %d, so there's 2 of them. So now we can take that and feed it into this macro called printf. Now there's a lot of code here, but the magic is really happening right there. So what this is doing is it's taking a type description and saying, hey, does the type description that matches this format specifier match up to the argument that you just passed me? Right? So here, this is where the logic is happening. So if it is a %d, then ask it if the current argument is an integer. If it is, go ahead and build a string. Otherwise, fail, error. If it's a %s, ask if it's a string. If it's not, fail. So we can do things like this, like so. And you get a compile time error because what I've done here is I've switched a string for an int. You get a compile time error that says that an integer cannot be used with the format specifier %s. This is not a language level error. I wrote this error right here. Right? And you can do things like here I have given the format string with no arguments. So that is also a compile time error. You get an error that says the number of format specifiers is 2, you've only specified 0. And that too is something that I wrote. This is not something that's coming from the language. It's right up here. So you have, at this point, in my opinion, a type-safe, more or less, printf. But I think that the real value add here is not a type-safe printf. Okay, that's sort of a parlor trick, right? In some ways, and really, like, I was kind of dogging on dependently typed languages before, saying that their kind of thing is printf. Dependently, a lot of languages can do type-safe printfs. Dependently typed languages just use that to sort of bootstrap you into understanding what they are. That's not all they do. So I was just kind of using that as an example. But what I think this really brings to this table is I can have user-customized hole-driven development. If you've ever used GHC, if you put an underscore somewhere, the type checker comes through and tells you at that point what the type of that thing is supposed to be. So it's sort of like this developer workflow thing. If you don't know what goes somewhere, just put an underscore, and it's called a hole, and it tells you what the type is. And I can do that for myself here in this format string. So here I have an underscore, and if the argument that I'm getting in is a string, I just say, hey, try %s. If it's an integer, try %d. This is what static introspection gives you. When you can introspect on the type of the thing that's being passed in, you can provide errors like this. So for instance, here, here's an error. Like this is saying, hey, I want to pass this, I want to print this string. I've forgotten what the format specifier is, and it's telling you, try %s. And it's an honest to goodness error, so it's actually even underlining it in my editor in the right spot. So I think this goes beyond a type-safe printf because it features what are essentially domain-specific user customizable holes. In my opinion, I really think about the interaction between humans and computers a lot, much more than I think about type systems and things like that. In my opinion, this closes the feedback loop between, somewhat closes the feedback loop between a computer and a user. Why do you have to Google this stuff? Like, it's just so weird to me that, like, the fastest way to get this information is to, like, ask some all-seeing eye of Sauron the question, you know, like, how do you print a short? And Sauron's like, %X, you know? And you're like, thanks, you know? Appreciate you hooking up the Shire with fiber, you know, that was great. You know, like, that kind of thing, right? So it's just so weird to me that all of this information is already sitting in your computer, which is a foot away from you, and you have to ask, like, the entire internet for the answer to something that's already there. Simply because your programming language hasn't given you a way of letting you query it for information that it already has. This is a problem with every typed functional programming language, for the most part. So, I'm going to close out a little bit. So let's talk about the problems. This is one of my favorite quotes. A good science fiction story should be able to predict not the automobile, but the traffic jam. So this is a science fiction story that I've told you right now. I don't know of a typed functional language that has, you know, sort of doubled down on static introspection and compile time evaluation. So here are some problems that I predict that you might have. So this isn't, like I said, this is not an evangelism talk. This is sort of a, hey, take these ideas, but here are some caveats. First, I'm not going to belabor the point about performance. Please measure it. You don't just get it, you know, just by using compile time evaluation. The other thing I'm really worried about is this loss of modularity. So now, because you can sort of statically introspect on one type and statically introspect on another type and sort of put them together, you can get these like horribly coupled types. And yes, you can refactor them because they're quote unquote type safe, but once you get to a code base of a certain size, they're only refactorable in theory. You'll just never do it. It'll just be horribly coupled. Like any like illusion of having modularity is just gone. And because you can introspect on just the bits of the object that you need, I bet you a temptation is going to be just to create this huge object. So you're just back to like some God object from like, you know, the mid-90s. So, you know, people will just keep tacking on to the end of something because they're like, hey, you can just query it. It's not a big deal. It's like just adding another column to a database table instead of like, you know, doing a foreign key or something like that. And one of the biggest things, especially coming from the type functional side, is that I think this completely defeats parametricity. So parametricity is the idea that, for instance, like if you pass a function an a lowercase a or something like that, it shouldn't be able to do anything with that except pass it out. So the idea is that like once you have parametric polymorphism, ID a going to a has only one implementation, right? But with static introspection, now it has infinite implementations. Because you can do anything with that a. You can reflect on it, do whatever you want. If it's a number, you can add one to it. So maybe the answer is you have to seal your types with some explicit unsealing. Maybe. And maybe that should be tracked by the type system. I don't know the answer to that. Maybe. So the other thing is I was talking about tooling support and how this is like superior to IDEs. But in some ways, it cripples an IDE. So given that snippet of code down there, so people can see it, it's just a proc that takes like some generic thing t, and it says when t is, what should the IDE do for that underscore? It can't possibly know what to fill in there. All it can do is give you every type that it has in scope, which could be an entire project that include all of your dependencies. There's no way it can possibly know what to put in there for you. It cannot predict what to do. So this completely cripples any predictive ability that an IDE might be able to have, if you go crazy with it. But in conclusion, I think it's still worth exploring. Because we need type-level reflection. We need these flexible interfaces. We need type-safe string formats, like printf. I had another example I don't have time to show you, where we have type-safe URIs. This is the same thing that like other languages provide for you as like type-safe URI routing and things like that. We can do it. We can just do it in a couple of maybe 20 lines of code. You need to be able to query your code base as though it was a database, because that, in my opinion, results in better and more flexible software over time. You need granular tooling support at the library and module level, because that takes the heat, in my opinion, off of the language designer. And really, they are they know the least about your application, and we're transferring sort of diagnostic power to people that know more about your application. Which is why I think that we should explore static introspection and compile time function evaluation. And that's my talk. Thank you very much.